It is time for null space. Null space. All right. This is in fact right null space. We'll see that later, I suppose. More clearly when we talk about left null space, but let me just say what that is. So this is our search for null space, right? And we're going to, which is to say we find all x such that a times x equals 0. We want to solve the homogeneous equation. This is, we're multiplying x on the right of a. So x is on the right of a. So we sometimes will say, this is left out, but it's really the right null space. It's the left null space is if we have a row vector on the left of a. Right, so that's good. Very badly when we do the drawings, the right null space will be on the left and the left null space will be on the right. That's unfortunate. But in terms algebraically, they're in the right spots, correct spots. Madness. So we're going to look at Physic again. This is how we do it. There's one principled way. Right, so I've just copied Physic back here. Right, there's our initial structure. We did this row reduction. Now, you don't have to, if you're just finding null space, you don't have to use the B's because right, for the null space of A, well, let me also put in here the right things. The null space of A, n of A. That's our notation. Sometimes a bit of a curly n, but that's what I'll use. So for the null space of A, we set B equal to 0, or start with B equals 0. Much easier, right? Better. We'll see that that's fine later on. That's what we'll do. So B equals 0 means all of this is 0. All of this is 0 as well. These things are all just wiped out. Okay, so 0 and 0 everywhere. So the D is also 0 as well. So this thing here is a 0 as well. And B back here is 0. So that's the plan. Let's make that a vector. Let's make this a vector, and then we're done. All right, good. So that's going to solve that's going to simplify our problem tremendously. We will just now use back substitution. However, I mean, in principle, right? That's what we do. We've got our row reduced form. It looks like a upper structure. It's much easier because we've made this extra effort with row reduction to create these pivot columns very strongly. So we'll see what happens. Let's see what happens. Okay, so let's just pull out the equations. Right, so now we have, right, so we just set the B equal to 0. Well, let me write that. This is what it looks like now, at least in the augmented matrix form. It's very simple. It's the reduced row echelon form of Physic and then zeros. Boom. Okay. So normal thing, usual story. Just here. Just for this next step. We just pull out the equation. The bottom equation is all zeros, right? There's just zeros here. Don't have to worry about that. Again, there's always a solution to the null space equation because 0 works. So we don't have to worry. That's always going to work. We're never going to get into trouble. So the top equation is this, and I'll put minus x4 over here equals 0. And then the second equation is just x3 plus 2x4 equals 0. All right, let's annotate a few things. So this is these two are the pivot variables. Right, they correspond to the identity matrix columns, right? We wanted these things to be like this. And then the x2 and the x4, these are the free variables. So let's look back at our equation, our reduced row echelon form. The only time x1 and x3 get picked up are here and here. They're the only time they appear, right? Because they have zeros in the rest of their columns. So they only appear once, so we can always when we write these equations, we can immediately express the pivot variables. Let me write these words down. Always do this. Do the following. Yeah. Following, and let me say, well-defined procedure. Express the pivots, and these are the dependent, think of them pivot variables. Let me write that, dependent, in terms of the free variables. So much good. You can do it. It's true, you can do it. There's a lot in this course, but you can definitely do it. And once you've got it all in your head, very pleasing. Very pleasing in terms of the free variables, but we must work hard to move up from being grasshoppers. Not sure what comes after grasshopper. Anyway, monks. Okay, so express the pivot variables in terms of the free variables. So I'm going to kind of outline that. So let's do it. So this equation becomes x1 equals minus 2x2 plus x4, and then the second one is x3 equals minus, well, let me put a 0, plus 2x4. Good, good. And then the next step, always do this too. x1, x2, x3, x4. Just write it down. Similar to what we had for column space, but this is, you'll see this over. Always do this. And then here, replace the pivot variables with free variables. All right, let's do that. So the pivot variables are here and here. So the free variables just stay, x2 and x4, right? And then let's put in these other expressions. So x1 is here, x3 is here. I don't think I've made too many lies. Yep. And then there's a 2x4. So there are only x2s and x4s here, just the free variables. So this is now something times x2 plus something times x4. Right, you can always write that structure out where the x2 and the x4 are elements of the real numbers. So the x2, minus 2, 1, 0, 0. Did I get that right? Yeah. Okay. Right. So this is. So if we look down through here, we find all of the x2 pieces here, and the rest are zeros. The x4s here, here, and here, and the other one is a 0. So that we get a 1, a 0, a 2, and a 1. And I think I should have. Should I have a minus 2? Oh, I've done a bad thing. Yeah, of course. So this is, right, when we put this on the other side, so let me get the right thing. So it's here and here. So let's, hopefully you spotted that. Minus 2x4, minus 2x4, minus 2. All right. Yeah. Okay, so, and where x2, x4 are elements of real numbers. So any vector that is a linear combination of these two vectors will get sent to 0. So a times, one way to think about this is a times this guy, minus 2, 1, 0, 0, equals 0. And that's true here as well. A times 1, 0, minus 2, 1 also equals the 0 vector. Let's look at it. So this says minus 2, 1. So it says minus 2 of this column plus 1 of this column. Yes. And then 0 of the others. Clear. And then 1, 0, minus 2, 1. So add these two together. So we get 6 and 12 and 24. And then minus 2 of this is 6, minus 12, minus 24. So that's true. They're not the, so then we can take any linear combination of them. That will work too. Again, it's a subspace. All right, so the formal definition, lots of victory here, people, lots of victory. And so you can, hopefully you can see that this will always work. We'll always have pivots, we'll always have free variables, always put the pivot variables in terms of the free variables, and then always have a line like, you always have a line like this. Seriously, yeah. You'll always have a structure like this. X equals all the entries in the vector. You know, we're not going to have X 73, so this is okay. Replace the pivots with the free, then explode it so that you've got the free variables multiplying fixed vectors. Cool? Cool. Okay, so we've got to do the formal piece. So formally, we want to write down what the null space of A is. So the null space of A is any X living in R4, right? They're four-dimensional, such that X equals, we'll just use what we had, X2 minus 2, 1, 0, 0, plus X4, that's a 1, 0, minus 2, 1. This is where X2 and X4 are real numbers. End curly brackets. Right, this is a set, turns out to be a subspace. And it's really built in here, right? This says take all linear combinations of two vectors. So this is, what is this? This is a 2D, it's a plane in 4 dimensions. So this is for Phasic, the matrix called Phasic, this is a plane in 4D, which is just, who knows what that is, right? That's a little hard to understand. But there it is. So it's a plane, so it takes a whole plane and just sends it to 0, goes zap, goes zap. This is something we have to, so notes, just 2 notes. So because n of A is not just 0, right? There's some substance there. If AX equals B has a solution, just using the better terms now, has a solution, which means what about B? It means B is, so i.e. B is in the column space of A, right? Lives in the column space of A. Then it's buildable, it's reachable, it's makeable. Then there are infinitely many solutions. So the null space governs this infinitely many solution story, right? Because if there's one solution, you can always add a null vector, right? If the null space vector is just 0, all you can do is add 0. But if there's just this huge, 1, 2, 3, 4 dimensional subspace of Rn, this is n, right? There are vectors that are not 0. Then you can always just add them to X, and you will still get AX equals B. Okay, so that's a big deal. And then soon, in the excitement that is matrixology, soon we will see, right, it's a 2-dimensional space that the dimension of null space of A in general is right like this. Dimension of null space of A is equal to n minus R. right? N minus R. So this is the rank again. Rank of A. And this is the number of columns. So in this case, number of columns. So for Physic, number of columns is 4, right? 4 across. 4 minus the rank, 2 equals 2. Two-dimensional. Wow. I know. Maybe you need to lie down, just recuperate a little bit after that excitement, and then come back, and we will actually we'll find a general solution for an arbitrary B for Physic, if such a solution exists. Okay, let's just cool off for a little.